Well, another day, another coding challenge. Um, Welcome everyone. This stream is for entertainment purposes only. And today we will continue my embarrassment and see if I can crack another problem under 40 minutes. So let's go to the lead code page and pick random problem. Okay, pick one. Okay, it's a medium problem now. Okay, seems many people like it, which is a good sign. Well, let's see if we can crack it. Right, given an array of n integers nums, a 132 pattern is a subsequence of three integers, nums I, nums j, and nums k, such that I less than j less than k, and nums I less than nums k and less than nums j. Return true if there is a 132 pattern in nums, otherwise return false. Follow up. Quadratic is trivial, obviously. Could you come up with near linear or even linear solution? We'll see, if at least near linear. Inputs, now 1, 2, 3. Output false. There is no 1, 3, 2 pattern. So the idea is, so the last element should be um, smaller than the medium element. So the medium element, so the element in the middle should be the largest. Then we should have at least one on the right side that is smaller than the medium one, and at least one on the left side from this medium element that is smaller than both. Alrighty. So input nums 3, 1, 4, 2, and there is a pattern, sequence 1, 4, 2. Makes sense. Minus 1, 3, 2 also works, yes. There are 3, 1, 3, 2 patterns. Minus 3, 3, 2. Should we return? We should just return true. We don't need to return all of the patterns. We just should check. So the constraints. And the length of how many numbers do we have is basically 10,000 from 1. Why do we need 1 and 2? Obviously, this doesn't make any sense. A number can be from negative billion to positive billion, anywhere in this range. All right, so let's switch to the whiteboard scene. So as you've been told, the quadratic is trivial, right? And what's the quadratic here? Let's just quickly describe the quadratic and then see how to improve it. So let's return to this interesting example. 3, 1, 4, 2. So obviously 1, 4, 2 is a pattern. So what would be the quadratic solution? All right, we pick element 1, say it's I, and then for the rest, we find j, we find k. So we find j until j is larger than I, in this case 4, right? And then we pick k, such that k, element k, is smaller than j, but larger than I, right? It's quadratic, it's trivial. So the problem with this is that it's quadratic. Okay, so first, all right, 1i for, let's say for I, do for jk and keep sliding, obviously. Now, so what we need to basically check, we need to check that there are at least 3 elements, right? Such that the indexes are, increasing. I, j, k, I less than j less than k. But the value is sort of goes high and then drops, but not as low as initial one, right? Because yeah, this is strict inequality. All right. So, well, obviously, instead of going through this, we can imagine we have some sort of priority queue, right? Uh, priority queue, or let's call it PQ. Yeah, let's call it priority queue, such that which is based on some numbers. So we start with what? With the smallest one, right? And then check. So in this case, it will be 1, 2, 4, 3. Then obviously we check indexes. So 1 refers to 2, 1, 2 refers to 3, 4 refers to 2, and 3 refers to 0, right? So having something like this, so we can retrieve element 1 and then see if what? Its value is, if we have something with larger indices, right? And then we retrieve, okay, so we keep retrieving. So 1, right? And then retrieve 2, it's index 3, right? So then we retrieve 4, it's index 2. And now we already have got the pattern, so we can stop and return true. True. So creating this priority queue will take us linear time. And then until it's empty and we retrieve 1, so this should be n log n, ideally. Like, let's imagine another example, minus 1 to 3, right? Where there is no such thing. So 1, 2, 3, 4. And we have 0, 1, 2, and 3, right? So what do we say? So we retrieve one element, and it's 1. Then we retrieve second one. So we start with the minimum one. It's 2, right? It's pointing to 1. This is pointing to 0. Then we retrieve third one. It's 3, 2. So there's still no pattern in this case. So then we retrieve 4. Or should we have two queues? One is based on indices, and another is based on values, right? So such that we retrieve first indices, and then no, I don't see, because once we retrieve 4, right, there is no easy way to say if there is a pattern, right? It's index 3, because we need to check 4 against 3 and 2 and 1 basically. So it's still quadratic in this sense. Interesting. Oops. All right. So what other options do we have here? Some interesting data structures, algorithms, maybe the per search or something. So let's imagine we have two queues now. One is sorted, sorry, just to see if it will help us. So let's say one is sorted based on the indices, and another one is sorted based on the values, right? I mean, we already have one that sorted based on indices, so we already have a right, and then we can have a queue, which makes sense, right? So again, 1, 2, 3, 4. So we start with 1, pulling by 1, and then we have this array 3, 1, 4, 2. So every time we pull element, and this we can, let's say, turn into the map, right? So key map value. So by element, we can retrieve its index. All right. So we know it's 0, this is 1, this is 2, and this is 3. So we can retrieve index by element in O1. So that's okay. We can do that. So we retrieve element by index, right? And then what? I don't see. So it's just three numbers, right? So we need to find basically at least one pattern. We don't need to find even all patterns. So it sounds like so we retrieve one. What do we check? Okay, it's in position 1. So we know we'll say assign it to I, the first one. Then we need J. That is sort of the largest one, right? Mm-hmm. Yeah, I don't see. So we also know that once we assign some I, we also know what J and K can be, right? Mm-hmm. So if I retrieve 2, which says it's 3, then what? I assign it to J, then K. Interesting problem. Right, I still have no algorithm though. Quadratic is trivial, you're right. N log n, which implies either some binary search or whatever. So if it's sorted, let's say we can sort it and have its indexes sorted in the same way, right? So we know which index is. Then, if it's sorted, we basically can, so we need the largest one first maybe, because it will be the medium one. Maybe not necessarily. Yeah, I don't see any cases except of keep iterating. There is definitely not the minimum one, because it might be the case that the minimum one is the last element, so we don't care about the minimum one. The maximum one can be the last element, so we also don't care about it in this case, because the largest pattern should be in the middle. But what do we care? Can we do it like a merge sort style? Like split it on sub-patterns of 3, because we know that we should at least have 3, right? Then if there is no, we merge them and then check again for the pattern. No, we again merge them, check again, and then the largest one. But if we can check this in the largest one, why do we need to split that? That's the question. So I don't see any benefit of having its, let's just, okay, we sorted, so what? So the last element should be in the middle in terms of size. And the middle element should be the largest. And it's not necessarily max, and it's not necessarily min. So, right. This is interesting. So far, it looks promising to have Q and the map and try to target this n log n, right? Priority Q and the map. So priority Q will give us elements starting from smallest to largest. And then every time we pull something, we do something. Right, let's try. At least we will see Q. I think it's this, right? PQ. Is it this? I think so, yeah. Yep, priority queue. And the elements, I guess, the same. Insert, maybe push, and top to access the top. Time of the largest by default element. And then examples. So we have priority queue, blah, 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 data, we put it here, and we start with 9 with the largest. So if we want the smallest one, which is Q2, data begin, data end, something like this, I guess. Oh, we even will use lambda to compare elements. Nice, like it. So in this case, some weird comparator, right? No, I think we are fine. It's just the maximum element. Then if not the maximum, that it's second maximum, and then we should check. Yeah, we can go with maximum. It's fine. Just push whatever it is. Print Q2. Or we can do just this one. So it's also fine. Right. CQ, we have vector, wind, and then we do the word greater. And we say it's PQ, which is nums end. Okay. And let's also have, we don't have alphabet here. Unordered map of int pairs, right? Which is basically what value value to index, or v to e. Let's call it v to e for simplicity. And then all we do is for const auto nums, we say v to e, not like that. Okay, let's do just regular int I, so it's more explicit. Less than what? Then num size I plus plus v to I nums I equal I. Got it. So now we have, so we don't need this. Now we have two things. Now we have PQ from min to max. And we have V to index. While Q, PQ empty. All right, so what do we do in cycle? Well, how about start with VI, right? Equal to PQ top, and then we do PQ.pop. So then I is what? Is V to I of VI. So now we have I and VI. But this will be quadratic if I continue removing this PQ, right? So then I can do what? Or maybe actually the maximum element at the beginning, such that we go left side and right side. So it's linear complexity every time we retrieve element, and starting from the max until we find something on the left and something on the right that is smaller than V. All right. So it's 3, 2, 1 pattern. Okay, sounds good. So then let's just make it more straightforward. Let's say PQ. Sure if it will allow us to do this. So let's just do another 4. Or actually, we already have 4, right? So we can just file it in one cycle 4, and then we do same PQ push nums I, right? So then we start with what? We start with the maximum pattern. So every time we retrieve its maximum, so it's the maximum is nums j. So the middle element. So it's vj, and in j v to index vj, right? Now, great. So now we need element on, so first First find 2. So we go to for int. Now this is k equals to j plus 1, and obviously k should be less than num's size, right? And k plus plus. So we find what? We find basically the maximum int max j, right? So we need to find the element that is the maximum on the right side, but on the other hand, it still should be smaller than, oh, it's k, max k. It still should be smaller than vj, right? Max from j plus 1 to int, but less than value of j, because value of j is the largest one. Right. So what do we do? If nums k, actually we don't need to say it's max k, we can just say it's vk, right? So to not confuse our terminology. Nums k is less, and we have about 20 minutes, 15 minutes to complete it, and it seems like we're almost done this. Nums of k should be less than vj, obviously, because we want it less. It's our 2, but still it should be the maximum on this right side, right? Yeah, then it's, oh yeah, it's very trivial. First find 2. It can be negative. So that's why it's not clear which one is this. So we're saying is what? Minus 10 billion, right? Let's just do minus 10. Right? So is this, so 1, 2, 3, right? 10 to the 9 minus 10 to the 9. So this is the minimum one, so it's fine to keep it like this. Obviously, it should be at least one smaller, larger than that, so we have I. So what do we say? We say that if nums k less than vj, vka is max between vk, value of k, and nums k, right? So we find the largest, but not as large as vj. And now, as you can guess, all we need to check is I. Find 1. So secondly, first retrieve 3, right, from the pattern. Secondly, find 2. Finally, find 1. And when we find 1, it should be up to j. It's called very conveniently I. That starts from 0, obviously, right? And then we iterate over j. All right. So this is obvious. Now we don't need vk. All we need to check that if, so vk is already to be guaranteed to be, this, right? If we can find value smaller than this, then we return true. If not, we return false. And obviously we don't need actually the whole one size greater than 2, right? Because if only 2 elements left, there is one of the smallest one. Definitely it can be 132 pattern already. All right, so if finally nums I is less than vk, our pattern here, right? If this happens, we happily return true. If nothing of this happens, we return false. And we can ignore these checks actually if nums is less than 3. But again, if it's less than 3, let's say it's 2 elements, we quickly fill out this thing and then just, this basically, we say it's logn, and this is on, right? And this is on. So the overall here is O and log n. Straightforward. So return false, return true, run the code, no time for debugging with the data, so we will debug it in this way. yj, it should be I, right? God. K is less than j, it's I should be less than j, what the k is. I don't know what the k. All right, so far so good. Obviously, these can be moved somewhere as a helper function. So we save a little bit here. Let's do this. Helper function to add entries to priority queue and hash map. Programmers be like showing stop sign. Description, this is stop sign, right? Okay, so it's void. Obviously, we don't need to return anything. Void view data. And we have this. And we have this. And all we do is basically this. So the only thing is, oh, we also need nums, right? So which is this. We can say it's const actually, because we don't change it. But then const will say, I don't like to access it. Okay, whatever. Let's see. All right. So, or actually we can just say this. And for this guy, we can dereference reference to push element, to assign element. So it should work. Let's check it out. And then always, yeah, we say field data. So we saved 2 lines of code in the main function. Not too much, but it is what it is. And v2I, and then we say nums, just nums. Verify 132 pattern. All right, now looks more prettier than before. What fails now? Nothing. All right, looks good. So if I make it const as well, because it feels like it may give us some extra points. Nah, just kidding. It won't give us anything. No, still fine. Submit. Let's see what we've got. Wrong answer. That's what we've got. Should be true because we have -1, 2, and 1. Interesting. All right. Which check is this? Oh, so it's 98. But I wonder why it doesn't. Oh, because of the map, right? Damn. Yes. It was stupid. So the map actually is dumb because we only use it once here, right? And that's it. And screws everything. So then we need custom comparator, I guess. And let's see, let's have only priority queue with pair of integers. Pair of int and int. Position and index. So that's my feeling, right? Index. All right. And then we don't need this. Then it should be this. Pair of nums I and say I, right? So now we need to figure out only the custom comparator for the priority queue. How do we do this custom comparator? Left to the power of 1 is Let's Stack Overflow a little bit here. Priority queue CPP for pairs. Priority queue of pairs. Example. Oh, it's make pair 1020. But it seems like by default it will sort. I put top first. Top. 10 to 200. Why? So start with smallest one or with the largest one? It's because greater. So by default, it will be the largest, right? Let's see if it's just as simple as this. Just make pair. All right, everything looks good. Let's see if this thing, once we say this, it's top first, and this is top second, and that's it. And you don't need map. Very simple. And it's even smaller now in terms of size. Let's see if code runs. Not sure if we need custom comparator for the pair though. V to I, what? Oh yeah. Nope, we don't need these things. And okay, something else I saw. This one. And go. One of the worst solutions ever. Just faster than 5%. Yeah, I guess everyone uses this one for 132 pattern, but at least we made it. We made it this time, and maybe slightly better. We can be slightly better on memory. So what we've got, we have just one priority queue that does this. Maybe pair is not the best, but at least it does what it does, right? Verify 132 pattern, and I guess we can make it 2 technically because yeah, definitely we don't need to check later. So one extra point could be potentially achieved here. So yeah, it's logn. Right, and this is n, so it's n logn. One more time. Still 14 megabytes. I wonder what's the linear solution though. All right, now we're worse in terms of time, but the memory is better. 10.6. Let's see if these two can be combined. This will be, seems like our maximum points today. And we're basically around out of time. Okay, we stop here. Cool, 40 minutes coding challenge done. So those are our points. Let's go back to the whiteboard. And finally, we've got some points here. Whew. So what do we have? Basically 5 points and 11 points. All right. At least better than less than 1. 11 points. So we total 16 points. Yeah, I think today is just a regular day. Nothing much interesting. Okay, so before we finish, let's jump back and just out of curiosity check what the heck was the linear solution. I'm super curious. It's Java, simple C++ solution. Let's see. Find pattern, this vector, if it's a return false, or yeah, whatever, we don't care. And reverse, and then while. You have some stack here, push back and forth. Yeah, I don't see like, it's not linear, it's 4 and then there is some while loop inside. How did it pass though? Don't understand. Should be like, yes, monotone stack. Use a decreasing stack to store the value. Decreasing stack. To store the value of num k and use a variable third to store the value of num j. Yes, the medium one, exactly. So the decreasing one, so we're going from maximum to minimum, right? All of it's basically what we did. It's basically what we did, except we use priority queue, and it seems like it can be done with stack. But then you need to sort it, which is still logn. I don't get it. And logn when you do sorting. Right, so initially what we do, yeah, the minimal integer, whatever, we start with this one. Inversely traverse the array to indicate the first value. If the first value is smaller than the third, then return true. If not, then put it in the stack. So num k is what? Num k should be less than nums j, yes. And k should be the rightmost element, right? So ijk. So what we say, so for the rightmost, we use stack, and then for the j, we just store the max one here. So we have just regular stack, nothing fancy here. Sort is this, right? All we do, we go from num size in the reverse order, basically, or whatever. And then you say, so we start from the rightmost element, and then we say, if it's less than third, return true. Interesting. And this is works? All right. If not, then what do we do? Until S is empty, in the first case, it's empty because we start with the last element. So we just push it, the last element, to the stack. Okay. So then we go to the next one. And then what we do? I don't see where do we stop. Nums greater than a stop. Yeah, that doesn't make sense to go further than that. I don't see where we modify the third one. Yes, we say third is as stop. So we move it to a stop now. So if it's not empty, if we had one element there, we move it to the top and then remove it from the stack. But the problem is that your third element that should be in the middle, now well, it's the index, looks like. Am I wrong? Mm-hmm. Mm-hmm. So then I will be the element that precedes the last element, right? The stack is not empty because it contains the last element. So we assign the last element to the third, and we remove it from the stack, right? So if nums I is less than third, we return true. I don't really understand. So what if we have elements like 4 and 2, right? Say that we assign the 3 to 2, and 4 we assign to, obviously we can swap them, so it still says that doesn't really matter. But I wonder, and also, how do we check that there is 1 somewhere at the beginning of the array? Because it should be 1, 3, 2 pattern. So it's still not clear how it passes though, but seems like stack is sufficient. So technically you don't need queue if you just do stack and reverse it. Interesting, interesting. Yeah, it feels like strange because who cares if you start with the maximum element or not, if you can just find something else faster. So yeah, I would imagine just relaxing these constraints so you don't need strict order, so you don't need to start with the max element all the time. Just start with some element and check left and right, but make sure that you have all elements sufficient to be large enough. All right, so that's it for today, and let's just do some fireworks because we technically solved the problem in time. Maybe not the best way, not the highest scores, but we did it. Right. Although, to be honest, I was a little bit confused at the beginning. I didn't get it. But sometimes you didn't, or it feels like you almost get it, and then, yeah, and then you start coding, and then you, this thing, yes. Nice. Okay, thanks everyone. See you next time.